Okay, guys, welcome back. We have another speaker, and this time it's David Whitney. When you hear Whitney, you think of a superstar. He looks like a heavy metal superstar, but somehow he managed to write 2 best-selling kids books. Life happens. Today he will talk about, as for all I know, his failures in life, and mainly bad stuff that happened recently during the quarantine years, and how that brought him to the success today. So, David, you're going to talk about building a Game Boy emulator in .NET Core, which is very interesting to me since I love Game Boy since I was a child. So, the stage is yours.
Amazing, let's do it. This is really a talk about my COVID-fueled anxiety and not drinking myself to death by trying to find something to do with my time locked in my house. Great. Super Mario. So I'm going to introduce myself first a little bit. So I'm David, and I'm an independent software consultant based in London in the UK. So I work for myself, mostly doing kind of mentoring roles and strategic work for UK companies. So I've had really pretentious job titles like head of engineering or chief technical architect, all those kinds of things, but none of that really matters at all. It all sounds a lot fancier than it really is. I just really love making things, and I really love the people that make things. And I think this conference is called Make Stuff, Build Stuff, not a product placement. So yeah, I've written a couple of kids' books about programming, but recently I made a Game Boy emulator. Yeah, weird. So why would you do that? First, we're going to start out by talking about emulation. Let's do a quick primer, really. So emulation is the practice of writing software on one system so that it can simulate the runtime environment of another with the goal of running software designed for a different piece of hardware or environment. So there are a couple of different approaches to emulation, and you probably use some of them before yourselves, really. So there's low-level emulation, where you implement the behavior of the raw hardware, and then software design for it should just work. And there's high-level emulation, where you attempt to run the software natively on your target platform, intercepting and re-implementing certain system-level calls. Now, most game system emulators are a mixture of these two things. They often emulate low-level hardware architecture while re-implementing things like 3D drawing calls in high-level modern APIs. Now, there are plenty of famous emulators, from games console emulators to operating system emulators, even to hardware emulators. If you're running any kind of virtual machine, you're pretty much that's an emulator, simple as that. So when I say I built a Game Boy emulator, what I'm really saying is I built a program that can run Game Boy software while the Game Boy software itself believes it's running on Game Boy hardware, which is a bit of a mouthful. Now, why would you do something like this? Honestly, it's all a bit pointless, really, but that's kind of the fun of experimentation. Now, there are lots of different answers to the question why, generally in life, but firstly, I honestly just wanted to see if I could do it. So often we're forced to live in this brutalistic corporate hellscape where only things that have to exist for money ever get rendered into reality. And this is literally the opposite of that. Game Boy emulators already exist. So if you want to play a Game Boy game on a computer today, I'm going to open now with, please don't use my software. Please don't. It's incomplete, it's possibly buggy, and I'm not going to help you wake the windfish in Link's Awakening. But this story is a little bit different and actually starts in the 1970s with Pong and an interpretive programming language called Chip 8. Now, we're going to use it to understand what emulation really is, and before we talk about Game Boys or Mario or Tetris. So Chip 8 sounds delicious, right? I started toying around with emulators as part of what I suppose now is a decade-long experiment in running coding dojos. Now, I do a lot of training for teams, and especially web dev teams, looking to upskill or pick up things like TDD. And when looking for different puzzles for dojos, I plundered the archives of the old website RubyQuiz. Now, RubyQuiz was great, and it used to run weekly programming challenges for things that you could learn to do. And I ended up running the Chip 8 kata there a few times. And what the Chip 8 kata is it provides a binary program written in the assembly language Chip 8, a machine language, and it tasks you with writing an interpreter for it, along with outlining the hardware the program was designed to run on. Now, Chip 8 has 32 opcodes in total, but the program supplied by the quiz only uses a subset of those opcodes to make it a little bit more approachable. Now, I remember thinking this sounded absolutely terrifying the first time I read it. Like, I literally stood staring into the middle distance, like, I can't possibly run this. Like, no one's going to do it. So, let's hold up. Machine languages? Let's look at a quick example of how computers, and specifically our computer processors, our CPUs, work before we go any further. Now, when processors are manufactured, they're built to implement a specific instruction set. Now, this instruction set is a list of things that the processor can do. Now, anyone old enough might remember the 1990s competition between CISC and RISC architectures. Now, what that stands for is complex instruction set and reduced instruction set, respectively. Now, these CPU instructions are what we're referring to when we say opcodes. The instructions are built into physical hardware and can be programmed using something called machine code. Now, every processor, or family of processors more realistically, has its own instruction set, and as a result, it has its own machine code. Now, machine code is a strictly numerical representation of the operations that a processor can perform. And an opcode, shortened from operation code, is the part of the machine code that specifies what a CPU should do. The assembly language, then, for a processor can be assembled into this machine code, and it's a low-level abstraction over the instruction set of your processor. Now, when we talk about assembly languages, what we really mean is programs written in the assembly language of the instruction set of your specific CPU. The CPU in hardware then implements those operations, things like adding two numbers together, or placing a number in memory at a specific location. And the opcode, when the CPU is running a program, tells the CPU which instruction to execute when it encounters it. It's fairly simple because it's this is the primordial goop of computers. I appreciate this all sounds really, really, really abstract. So let's look at this example above and we'll work through it and explain how it works. So on the left, you can see some raw machine code of a Chip 8 program that we're going to come back to a few times. And the same machine code decompiled into its corresponding instruction set on the right. Now let's break this down a little bit further. Break it down. Beside the opcode itself, most instructions also specify the data they're going to process in the form of operands. Just think of them as the parameters that get passed to an opcode. And normally, these parameters are a memory address or a register on the CPU, and a register is just some memory that's on the chip itself. Now, a memory address is just a number, and it's normally expressed in hexadecimal, but they're literally just numbers starting at 0, counting up to however much memory you have. Now, when people talk about how many bits a CPU is, what they're referring to is the largest number a computer can hold in its memory when expressed as hexadecimal. Now, the more bits, the larger the total amount of memory the CPU can address. A CPU, for example, that can only understand 8-bit numbers can only understand the numbers 0 to 255. Therefore, it can address 256 memory locations. Now, a CPU that understands 16-bit numbers can understand 0 to 65,535, which means it can address a total of 65,336 memory locations. Literally, the bigger the number, the more memory it can reference. Now, each memory location can store an amount of data, and in the case of Chip 8, each memory address is 8 bytes of data, and the Chip 8 hardware itself has 4,096 memory locations. Now, I can come and give you a degree certificate if you like, because this is like the whole of computer science, 3 years in 3 slides. Right, you're done. It's the foundation of everything. So when you're running a high-level programming language like C# or JavaScript, the runtimes that execute those programs have been specifically compiled down for your CPU architecture. This means that ultimately, somewhere, something has been translated down to machine code and executing on your CPU. And wherever you create variables in your programs, somewhere, something is putting things in memory. It's all buried under like loads of abstraction, and most memory manipulation is done by interacting with the operating system. And then the operating system decides what lives where in memory, but this process happens for literally every line of code that you ever write. So, after our crash course in how computers work, let's take a look at the Chip 8 program again and some of the opcodes that it uses. Now, the program in the top left portion of the slide is the original Ruby Quiz Chip 8 test program. It's just a raw binary file, and in the machine language of the Chip 8 computer. So when you open this in a hex editor, that's what it looks like. Now, to interpret this program, you would loop through each of the bytes, and if you take a look at the C# snippet to the left, we're just loading this file as a byte array and printing it out on the screen. Now in C#, the bytes are all represented in base 10, so as integers. But notice how the first number that gets printed, 97, is 0x61 in hexadecimal. And if you look at the first two digits of the original program at the top, this is the same 61 from the very start of the test program. Now our documentation shows that our Chip 8 interpreter operates on 2-byte opcodes. So to run this program, we need to loop through each of the pairs of bytes. In this case, we read 61 and 77 together, the 2 bytes, and then we process them according to whatever the hardware behavior needs to do. Right? This is how emulation works. So let's zoom really, really tightly in on those 2 bytes in the file. Now the 2 hex numbers, 61 and 77, they make up an opcode and its operand. So this is expressed as 6xkk in the documentation. Now this opcode is explained in the original Ruby quiz as setting the memory location x to the constant value kk. So in this case, 6177, kk is the 8-bit constant, literally the hexadecimal value 77, which is 119. That's the number in decimal. And so our first opcode says 6. That's the opcode. 1, a constant, the memory address 1, and 77, the decimal number 119. Now that translates in a sentence to put the hexadecimal number 77 in memory location 1. So if you imagine memory locations like an array or like a big Excel spreadsheet or something, you can interpret this entire Chip 8 program by implementing each one of the opcodes and writing some code to perform whatever operation it's meant to represent. So with different opcodes, like 6 in this case, would do different things. Right, so this is a really scary looking problem, right? Really, really scary looking problem if you've never done anything like this before. But it's not so complicated when you really start to do it, right? It's really just a big switch statement. So because it was so far out from what people normally find themselves working on, people attending these dojos always found it exciting when they made some progress. It was like, oh my God, this is magic, right? And I ended up running this particular dojo a lot with plenty of different audiences because I think there's nothing more fun than taking people who think their only real skills are getting a number from a database and putting it on a web page and showing them just how capable and awesome they can be with a little bit of lateral thinking. And that really programming isn't just this horrid, blunt, commercial, boring thing. Like not everything has to be about business value, right? It can be fun and intellectually challenging and enjoyable. The end. No, I'm joking. Right, now you know how to write an emulator. End of demo. No, Gameboys. Let's talk about Gameboys. So Chip 8 is a useful introduction to this kind of low-level programming because there are only 32 relatively simple opcodes to implement. The Ruby quiz kata, even more so because it only uses so few of them. And honestly, like if you want to get into this, this is definitely where I'd recommend you start. Because I think it's important to remember that anyone can do things like this. I'm not a particularly incredible programmer, don't put that on the internet. I can read and I can reason. And I really wanted to know if, given a background in building smaller machine code interpreters, I could do something bigger. So Gameboys, right? A little bit bigger. What's a Game Boy? Like literally nobody asked that question ever, but I'm going to tell you. So the Game Boy is an 8-bit handheld console manufactured by Nintendo. the first handheld in the Game Boy family. It was released in Japan on April the 21st, 1989, and then North America 3 months later, and then a year later in Europe. It was designed by the same team that developed Nintendo's original Game & Watch and several of the original Nintendo Entertainment System games. Now, I mean, we all know what a Game Boy is, right? They're literally iconic. You can set them on fire and they still work. Like there's one in like the New York Nintendo Museum that has literally been set on fire and still works. They saw off like 50 billion competitor consoles by being simple, accessible, resilient, and fun. Like, this is my childhood in a little plastic mold, honestly. This is where my lifelong obsession with video games probably came from. I literally just typoed game from in my speaker notes when I wrote this. Game Boys are awesome, like honestly, really awesome. And personally, I remember growing up in Asia in the 80s and getting my Game Boy from the Temple Street night market in Hong Kong. And I was always like so excited to go down through the night markets looking at these stores of really, really colorful boxes, beautiful box art. And not only is the Game Boy awesome, it feels like kind of deeply personal to me. Like it was very much like my mother used to lock it up in a cupboard so I wouldn't spend too much time playing games. Look at where I am now, Mum. No, really, what's a Game Boy? We don't care where you bought your Game Boy from, David. Programming. So what is a Game Boy? Fine. So a Game Boy has an 8-bit 4.19 megahertz CPU, 8 kilobytes of RAM, and 160 by 144 pixel display. The CPU is similar to an older Intel 8080 CPU, and most of the assemblers use a Z80 style processor syntax. It's a custom chip, but the instructions are similar as other well-known processors. So, I read those technical specs and I felt emboldened. Just like the Z80. They're well old. How hard can this possibly be? How hard can this possibly be? I adore games, I always have. And I love the 90s and 2000s emulation and porting scene. But there's a few things specifically set me down this path on this particular occasion. Now, I watched this great YouTube video on the Modern Vintage Gamer channel, where he did a time-lapse of a port of the game Another World to the original Xbox. And he did it live on stream, and I'd spent some time in the past transpiling and transliterating software for various clients in my job. So I ported Python to Java, .NET to .NET Core, Java to .NET Core, C# to Java, C# to TypeScript. And I felt quite confident being able to convert things between programming languages. I'd also been working on some C and C++ hardware projects around wearable displays. So I kind of thought, hey, Z80 processor isn't too different from Chip 8 in complexity. Totally not true. I wonder if I can write a lo-fi Game Boy emulator that I could use to capture frames and put it in some kind of wearable project of some kind. I thought that'd be pretty awesome. And so I fell down this black hole of 1990s era PDFs about reverse engineering Game Boys. You know those like Wikipedia black holes that you fall into and like don't get out for 4 hours? Well, this one runs deep. Yeah, the 90s were wild. I spent about a day reading something called Pan's Docs, a 25-year-old long community effort to catalog all the details of the Game Boy hardware. This is like some peak 1990s era deep technical unpacking and reverse engineering of the Game Boy. And it's a head full, certainly, like it really is. They're wonderful docs. I'd probably not recommend them as a casual bedtime romp, like not the one. No plot, the characters are boring. So I skipped to what felt like was the most interesting place to start, loading some information from cartridges. And I opened Visual Studio, and I started to code. Now, while from the frame of reference of writing an entire emulator, parsing a cartridge might not seem like much of a big deal. But I managed to get it done pretty quickly. Now, I grabbed a copy of my totally legally backed up ROM, I promise Nintendo, don't sue me, of Super Mario Land. I managed to parse the boot logo out of the cartridge, and the cartridge information and the metadata within like 3 hours of hacking around. Like that's literally some code I copied from it. And it felt real. It felt exciting. I had some virtual memory, I had a CPU class, I had some OPCODES. then I got stuck. Like really, really, really stuck. I felt like I had a reasonable grasp of the Game Boy hardware, but I couldn't understand why some of the opcodes weren't working. I couldn't work out what they were meant to do, and my emulator kept crashing in its boot sequence. Now, to make matters more confusing, the documentation had randomly, halfway through, started using notation I did not understand. Like, I'm not a mathematician, and I think it was some, like, galaxy brain math stuff. And I couldn't do it. I'm sure it's high school maths, but I couldn't do it. And I was trying to implement the opcodes for the CPU, just like in our earlier Chip 8 example, and I just kept getting lost in the documentation, and I felt helpless. But not to be deterred, I went hunting for some other code bases that have been here before, right? Like in an attempt to find something that could help me understand the notation in the documents. Now, I found a couple of emulators that worked in a couple of different languages. You know, people have built Game Boy emulators before. And I stumbled upon a working project called CoffeeGB, a working emulator in Java 1.8. So this was wonderful. A clonable repository that I could reason about in a language that I understood. At that point, I figured I could transliterate this MIT licensed code base, use some of the open source test suites, and kind of glue the things together. So I started off by losing an entire day converting CoffeeGB to Kotlin. It worked, but there wasn't really a point. I thought it might look closer to C#, so it would be easier to move code between. And then I decided to commit to doing a like-for-like transliteration of the Java source into Netcore 3.1 in an attempt to hopefully understand where my opcode processing approach differed. Translator what now? Yeah, so I keep on using the word transliteration, so let me explain exactly what I mean when I use it. This is originally a language term meaning to write or print a letter or a word using the closest corresponding letters in a different alphabet or script. Now, for a little bit of clarification, transliteration, as opposed to just a port, is a line-for-line cosmetic-only change. You can change the absolute minimum required to get the software compiling in the target language. Now, and then you do subsequent second and third passes to port the things that are missing or don't convert like for like. So porting and transliterating software is a very specific discipline, which is counter to how I'd normally build software. And there are 3 passes. So firstly, you need to transliterate it until it compiles from the entry point down, and this normally involves starting at the main method and only migrating code that gets called file by file methodically. Secondly, you then port over any test suites once the transliteration is done, and then you ensure that the tests in your target match the original in the host language. And then thirdly, you convert the code to be idiomatic. Now, in the above example, you can see how the Java code is subtly changed to C# with package declarations swapped for namespaces and attributes removed. Now, later, much of the syntax is converted to C#8 using expression-bodied methods. And this is a fairly trite and succinct example, mostly to fit on some slides. And some of the other conversions that you have to do end up a lot more dramatic. Now, this might seem like a set of really obvious steps, but you have to do some really, really unnatural things sometimes that like totally will go against all of your instincts. So during the first phase especially, you often find yourself fighting your tools because you're at a disadvantage if you diverge the code in any way that prevents a like-for-like comparison. So this means you have to do things like keep all the naming conventions of the original language. You keep the casings and the odd, non-idiomatic qualities of a foreign code base. Now, you need to leave them precisely as they are until you get to a point of safety. You also have to get very comfortable throwing not implemented exceptions like literally everywhere, where a direct equivalent is not available until you've managed to get the code executing. Now, the sooner you can start transliterating any available tests, the better, because you'll know early on if you're going to go off track. Now, ideally, you have a good enough reading grasp of the source language and a relatively advanced grasp of the target language to be able to convert some of the more subtle differences. In this particular code base, for instance, Java has rich enums. And they often have behavior loaded into them, which is totally not how enums and C# work at all. So producing similar syntactic constructs that could be used in the same way is quite important. And that requires a reasonable mastery of the target language to pull off without getting yourself in some weird non-compiling state. So once I'd found my groove with transliterating the CoffeeGB code base, and a couple of things became apparent. Firstly, that the UI would just not work at all, just wouldn't work. Not trivially, and it was because it was a bunch of Java JWT code, Java windowing toolkit. And there was absolutely no point in trying to convert that like for like. The JWT code, however, was responsible for both drawing the game on the screen and handling the controller inputs. So fine, 2 things on the list that you've got to rework. So my first target quickly became to get the Game Boy running in a headless mode, which was present in the original code base, just booting a Game Boy cartridge. Now, headless mode was designed to run the emulator without visual output or controls in a console window. I figured if I could do just enough to get it running, that I could port the unit tests that exercise some community-authored homebrew ROMs that are designed literally to test the various aspects of the Game Boy hardware. They've been built to build emulators. Kind of awesome. So I deleted all the JWT code, and I maintained all of the code paths that called into it, replacing their method bodies with not implemented exceptions. I implemented a few of the interfaces with empty implementations and managed to cajole headless mode into life. You can see the code for headless mode as it still exists today in the source code, passing in a null display and null controller and null sound and serial endpoints, along with, amusingly, the remnants of some JWT code left commented out for reference. I can't state enough how well compartmentalized the original code base was. And I was very, very lucky when I came to writing a new display. Now, the original code kept an internal array of pixel colors packed into integers that the various graphics display opcodes produced. So I just had to convert that array into XY coordinates and just find a way to quickly get the pixels on the screen, right? So I extracted the RGB, red, green, blue values from this packed integer and raised a C# event every time something happened on my new bitmap display class. So to match the original implementation, the display is run in its own thread and refreshes distinctly from the CPU that's also iterating. I just needed something to subscribe to now my event and do something with the pixels. So I use WinForms. Everyone's like, what? Really? Yeah, use WinForms. Great. You heard me. I ported a Game Boy emulator to .NET Core 3.1 to run it in a WinForms UI, and I'm not sorry, and I'd do it again. The number of questions I got firstly, sanity, why I wasn't using WPF, if anyone still used WinForms, if you could even run WinForms on .NET Core. It was excellent, truly. People forget that WinForms was literally designed to be easy to use and to be used in like rapid application development scenarios. And it lets you get stuff on the screen really, really quickly. WinForms is secretly kind of awesome. And it does run on .NET Core, actually, as of version 3.1, and it just works. Windows only, though, obviously, because it'd be well weird otherwise. So about 200 lines of code later, and I had a WinForms UI with a picture box on it that could update with every frame when every time the emulator raised the event to deliver one. And if you're eagle-eyed and look directly at the background images here, the other nice thing that came for free with WinForms is I got input handling, much like the original JWT version. I could just hook an implementation of a fake controller into the WinForms key press events. And it worked. Kind of, sort of. So once I got to the point where I had the title screen of Mario booting in C#, and then side by side, the original Java code base booting the same game, I realized that I'd made some kind of terrible error where my game would crash as soon as the game started. Obviously, enough of my port was working to get things on the screen, but establishing where my code had diverged wasn't very simple at all. Luckily, I'm not the first person to ever try and write a Game Boy emulator. So there's a really great set of homebrew test ROMs that I mentioned before that exercise parts of the Game Boy hardware that I could run in both emulators and see where they diverged and broke. They're wonderfully named Blarg and Mooneye. Excellent, right? I think the latter set of ROMs are from a working practice Rust emulator at the moment. So I ported the test harness across from the original code base, and I got the test ROMs running in both of them. And as I suspected, tests that were passing in the original version were not passing in my code base. This was an amazing first step. You know, literally I had failing tests, and I just needed to find out what had broken. Now, these are both low-level emulators, and they literally implement the opcodes of the hardware, and they tick at the clock rate of the CPU. The problem with that is you can't meaningfully step through the code. At 4.19 megahertz, that's thousands and thousands and thousands of ticks a second. So because you can't step through the code, that's okay, right? We live in Visual Studio. Surely there's stuff we can do, right? There are tools. We have amazing things like conditional breakpoints, right? Cool. They can break into the code when some variable changes, right? Now, ironically, the performance overhead of applying conditional breakpoints to my virtual CPU register was so severe that I couldn't even get Visual Studio to process the first test case as far as an error in less than 10 minutes on a high-spec desktop. Like, literally unusable feature in this scenario. I knew that if I could get both code bases in a breakpoint where their memory states diverged, I could solve the problems I was seeing. I just wasn't sure how to do it. Now, I was suffering from the pain of integration tests being my main tests. And it's funny how things that I would normally deal with in work were absolutely apparent at this scale. So I ended up spending a morning building two tools. I started by building a debugging tool that I built a client for in both Java and C# that would keep the ticks of both of the emulators in sync, breaking them both into the debugger when their memory states differed. Now, both emulators would call a HTTP server with a hash of their current memory state, and when it differed, it would tell them to both pause, which seemed like a really great idea. But in practice, it only helped me find one small bug because it was too slow to use meaningfully. You know, if conditional breakpoints won't work, I think I was on a bit of a wild one to think making a HTTP call would be faster. Too much overhead. So I went lo-fi. I built a logging function into each emulator that I could wrap around the test cases that dumped the entire memory state to a massive text file at every CPU log, every CPU tick. I knew that when the test passed in the first emulator, I could just hit stop really quickly in whichever one, you know, in the other one. And I could stop it if it was still executing. So I ended up doing a lengthy diff of these many gigabyte long text files to find the tick where the tick number where the emulators diverged. Now, once I had a tick number, like I literally just put an if statement in my code that said if tick is whatever, debugger break, right? Like really, really lo-fi stuff. And you know, it worked, right? It was important that I kept the transliterated code bases close to the original until at least the test cases passed and failed equally. Because if I diverged them too much at this point, debugging would have just been impossible. It would have been a nightmare. So the first bug I fixed this way honestly felt a bit like magic. Like I really did sit there like, did I just build a debugger and it worked? What? Properly wild stuff. So there's just this certain sense of accomplishment of like building debugging tools and actually working. It took about a day's work, but I got my emulator in parity with the original CoffeeGB source code so I could start refactoring it. So what was the crashing bug? I fell foul of converting one of the Java data structures into C#. Now in Java, as I mentioned before, enums can have methods on them. And I'd hastily transliterated some code that categorized enums for the different banks of memory in the Game Boy. Now, you'll notice if you glance on the slides here that the enum names used to categorize different parts of the same type of memory. So for instance, ROM_MBC3 and ROM_MBC_RAM are both identifying parts of memory that make up MBC3, a memory bank controller that's part of the Game Boy cartridge. So Game Boy cartridges use memory banks to expand the amount of memory available to games, which is interestingly why back in the day the size of the cartridge was used as a marketing point on the boxes, like, oh, 4 megabytes. Games with more data and more switchable memory banks could be larger, and normally the memory was used to store more graphics, right? So it looked cool. Now, the code in the emulator that implemented the opcodes to switch memory banks needed to check if the current memory location was part of one of these memory banks. Now, the original Java implementation used a regular expression to check if the name of the enum member contained the name of the memory bank it was looking for. Now, I hastily replaced that with a string contains call that presumed that the enum member would always have an underscore followed by MBC followed by an underscore, which works perfectly well for the string rom underscore MBC3 underscore RAM, and way less well for rom underscore MBC because there's no trailing underscore. So while trying to switch memory banks, my code was failing. And that explains why when my emulator could boot up, but when I hit start, it tried to switch the memory banks out and it would crash. So I quickly replaced my string contains call with the original regular expression to fix the bug. Likely there's way more idiomatic C# ways to do this, but I just wanted to get it working. So one of the final entertaining surprises was the afternoon I lost trying to work out why my emulator was slow. Now, I spent what felt like an eternity trying to profile the performance of the emulator because I couldn't work out why it was performing so slow and so badly. And the irony is because it was being observed. The program was ticking so fast that the overhead of collecting metrics and debugging slowed the program down. Like there's a theme here, right? Simply compiling and running the code in release mode without a debugger attached showed it running perfectly fine, and it was exactly as benchmarked. I might have skirted around the audio in the emulator because there is no audio and I haven't written it and I don't know how. So I've not written audio yet. So I've never really done audio programming before. And I'm looking into some audio wrappers in .NET like NAudio to make this work, to work out how to make the Game Boy sing. So throughout the first couple of weeks of this project, and given that we were all in quarantine, this was very much a quarantine project. I'd been teasing the internet with screenshots of Game Boy games relatively hard because I love a good bit of hype. And once I got to the point where the UI wasn't crashing and the code was suitably ported, I just put the emulator on GitHub and shared it around the internet. Mostly for the fun of it, honestly. And generally, people have enjoyed seeing this kind of project in C#, rather than just, I built another business application. And I stuck a ridiculous ASCII art renderer on the command line because who doesn't want to play Game Boy games on the command line in ASCII art? Why would you not want that? And really, that was the reason for doing any of this at all. C# is a language I deeply love and I feel very comfortable with. I love the direction of .NET, kind of core and 5, 6 onwards, and I'm on a bit of a journey at the moment trying to prove that literally anything you can do in other languages works in C# too. At least as performantly, and often plenty more beautifully in code. I think that's important. And it's wonderful to see other people feeling the same way, though obviously it wasn't without its detractors, because this is the internet, never read the comments, they say. But I always like to engage. And there was this one comment that both stuck with me and I thought was important enough to highlight. Reddit, as ever, is a mixed bag. I think that puts it lightly. And I had a bunch of really interesting conversations with people in like r.net and the C# subreddits. The general programming subreddits, on the other hand, not so much. Not so much. It's easy to forget how hostile people can be to absolutely nothing at all. Right, absolutely nothing. And legitimately one of the takeaways of this process for me was this. As programmers, we can be short and snipey, and we can dig through code contextless and take swipes at things and bring each other down, and it's not really very important, right? So let's take a look at this comment above. Everything in this comment is true. Everything is true. Totally could be better. I'm obviously a terrible programmer. I shouldn't ever put things on the internet. But you know what? Program consumes 30 to 50 megabytes of memory in total. I benchmarked it. And I'll do all this again in a heartbeat to put something cool and working out into the world for people to enjoy. So loud and clear, no gatekeepers, no perfection, doesn't exist. Do the fun thing, enjoy yourselves, share stuff. Or we let bores like that win. Like, we let those people win if we give up. So luckily, the bores never win in the face of people doing cool stuff, right? So within a day or two of putting some tweets out with links to the code, I already had a couple of pull requests. I had someone implement a monogame UI to let the emulator run on mobile devices, one with an Avalonia UI to give it a cross-platform user interface for Mac and Linux, as well as the existing WinForms UI, because WinForms will never die. The WinForms team don't pay me for this. Maybe they should. And a cross-platform headless command line interface thing. You can also reference the emulator as a library from NuGet and run it in your own projects. And that's the really cool thing. Like, I saw like a guy contacted me because he did a Twitter plays Pokemon that used this emulator, where you could tweet key presses at him and his user picture would update with a different bit of the Pokemon game. That was really cool. I know Scott Hanselman did some stuff about it on his blog. Like, people took this and built a much more interesting thing than I ever thought I would, because I had the nerve to not give up and I had the nerve to fail. So I'm happy that I didn't give up when I got stuck. And I don't think what came out of it was what I expected. That's fine. I know it sounds trite, but everything we do in software is built on the shoulders of other talented people that built things before us, and it's easy to just get stuck and give up. And it's hard to go on and decide to look around for inspiration. So I'm thankful for the wonderfully high-quality Coffee GB code base that I had the pleasure of adapting and merging with my own efforts. I'm really happy that I didn't succumb to my own hubris and decide that if I couldn't just work it out on my own, that it wasn't worth doing. And I'm absolutely thrilled that by sacrificing that little bit of ego, that something cool and fun that people can play with now exists. So I hope maybe some of you will play with the code and have fun. You can find me on the internet in all of these places. Feel free to tweet at me, hassle me, buy my books, any of the above. We can do shots in the bar, it's fine. Thank you for coming. Really, really appreciate seeing everybody. It's great to be back in person.
Thank you very much, David. Would we have any questions in the audience?
Stunned silence.
No. The producer told me that when I'm not here, they're very brave to ask
really
questions.
Chatty. I love you all. Come back.
Anyway, we have an online question. Deville is asking, have you tried programming in assembler language? If yes, what kind of programs did you create?
I have never programmed in an assembly language, and I had to learn it to do this.
Well,
terrifying.
That's that, Deville.
That's terrifying.
So, if anybody has questions, he wants questions. Look at his face. Such a puppy.
Vaguely intimidating aura.
Not at all. And seriously, look at you. You try. You
I
tried.
tried. Thank you so much.
Then.
Thank you so much.
We have a question there. That will take time, but we have time. That's what you get for hosting your event in cinema.
I love it. I feel like a film star.
Yeah, that's a huge place.
Really cool project. So I'm assuming you're going to continue with this kind of stuff. So would you share your ideas for your next one? Or are you still continuing on this one?
Okay, so I don't really know if I'm going to finish it, truthfully. And I think that was kind of part of the journey for me, was understanding that like I didn't have to hold myself to those standards of like, oh, this has to be perfect, it has to be finished. I want to get the audio done because I want to learn how to do audio programming, and I've never done it before. This was part of, I did 14 projects in 12 months during lockdown, and this was one of them. So I followed this up by making a 3D renderer by hand, and I had to get a maths textbook to make up for not doing A-level maths at school. So yeah, it's kind of a part of a series of things which I can probably characterize as projects that probably aren't worth doing but are fun anyway. So next, I'm not sure I'd write another emulator. I think I want to finish this one before I try that. I want to extend the 3D renderer. I'm doing some hardware stuff at the moment because I kind of want to get back to the original goal of this, which was to take frames from Game Boy games and make them physical. I want to blow them up onto a big LED display so people can play games together and stuff like that. That was the original goal when I set out to be I wonder if I can just get a bit of Tetris on a t-shirt. This is basically a talk about the world's longest yak shave.
Okay, you mentioned that you like to play video games.
Uh-huh.
What platform?
What platform?
Yeah.
All of them. I'm non-Partisan.
Okay, and when did you start playing games? What year?
1989.
I know you're 21.
1989. Shut up.
I started earlier than you. And I mean...
But, the Game Boy was when I started, honestly. I'm not going to knock this off the stage. I love games. I love game design. I think it's really fun. It's not my job, but it's...
No. I was just wondering what kind of games you like, what you're playing,
what I'm playing at the moment. I've been...
What's your go-to game?
I play a lot of Sea of Thieves. I don't know if anyone's heard of that. It's like a pirate co-op game because I love co-op. I like playing with people. Love playing with people. No, it's brilliant. I role-play a pirate on the internet. It's depressing.
I mean, you role-play pirate on the internet and in real life in some points. Look at your hair.
Exactly.
What do we have here? I'm not sure if it's a question, but Andrew says, I would love to hear Metallica Unforgiven coded into ROM and played through .NET emulator when you actually implement the audio.
You're on.
So that's an idea.
You're on.
And since you like cool things, I suggest trying Rockstar language. Here's a code. You can check it in chat.
Did Dylan type that? Was that
No.
No.
Okay. Anybody? Questions in the audience? Not really. Okay, so that's all. David, thank you very
so
much.
much.
Thank you for your... Well, that was quite a personal story.
They all are.